So go ahead, Karen.
So I think you should be able to see my title slide here.
Yep.
Yeah, so thanks, Michael. I am a master's student working at Waterloo with Michael. The stuff that I'm going to be presenting today is not only some of the stuff that I've been doing, but also the work of an undergrad working with Michael, Anya Forrestel, as well. So this is just a little recap of stuff that Adam mentioned yesterday. So we know that galaxy evolution is driven by their star formation. And as shown in these diagrams here, we know that the stellar mass function of the star-forming galaxies doesn't change as much over time as the quiescent ones do. So we do see a buildup of quiescent galaxies. And so this implies that there is a motion that is turning these star-forming galaxies into quiescent ones where they're no longer forming stars. And so this is the transition that we're trying to look at when we're talking about these transition galaxies. It's trying to capture those galaxies that are kind of in the middle. So this is a little diagram in color space in order to get an idea of what I mean. So if you have galaxies in that star-forming cloud and they're moving to the quiescent cloud, we're trying to capture those that are in the middle where they're partway through their transition, where they're not fully star-forming and they're not fully quiescent, they're somewhere in between. So we set up 3 different transition populations that we're considering here. So we have the post-starburst galaxies, which I'll talk about later, along with the blue quiescent galaxies and the green valley. And so the idea here is to compare these 3 transition populations in both the cluster and the field in order to get an idea of what's happening in this transition. So starting with the post-starburst, we're defining these spectroscopically just as Adam did when he talked yesterday. So this is using their delta BIC criteria that Lindsay mentioned. So this is picking out features that strongly, or picking out models that strongly favor an O2 emission, along with their D4000 break. And so these are meant to be the population that are no longer star forming, but were recently. And so you can see in their spectra here that I pulled from Adam's paper that their signature shows evidence of this. So when you compare it to the star forming galaxies, these don't show the prominent features of being star forming, although they were recently. So the next population that I'm considering is the green valley. This one, instead of defining it in UVJ space like we define the typical quiescent and star-forming clouds, we're defining them in near UV V space, near UV VJ space. This is just to separate out better that vertical separation between them. So we're picking out this green band in the middle. So yeah, you can see here that this would just be capturing all of the things that are moving from one cloud to another one, and we stretch it all the way across this diagram in order to capture anything that's moving regardless of how. And for the blue quiescent galaxies, this is a term that we came up with in order to describe the blue end of the quiescent sequence. So this is a picture from Belli et al., where they're showing that based on different quenching mechanisms, galaxies are passing through the blue end of that quiescent cloud on the top here. So we're selecting out that region and calling them blue quiescent galaxies because they would be just entering the quiescent cloud. So when we're looking at the Go Green post-starburst, we're selecting them based on their O2 features and their D4000 break, just like Adam had done. And they seem to be doing a pretty good job at picking out post-starburst-like things. As you can see on the bottom here, we get spectra that are very similar to what Adam had gotten for his post-starburst as well. So you can see pretty apparent Balmer lines and a fairly strong H delta as well. And when you compare that to Adam's spectra here in the green, we see that we get similar things. This plot up at the top here is from Anya. So she was looking at the post-starburst galaxies in phase space, similar to Muzzin et al. As well, where she finds a fairly similar distribution. The idea is that we'll be able to compare the distribution of these spectroscopically identified post-starbursts with those that Adam found. And then also compare the differences between this population, the Green Valley, and the blue quiescent galaxies. So when we're looking at the Green Valley, Michael had stacked their spectra here. So this shows pretty strong H delta as well, with O2 emission as well. We're selecting this in color space, and so based on that color selection, this is an unexpected. And when you look at individual spectra, some have low O2 emission, but mostly we're seeing it in them. So the thought here is that they are in fact doing an okay job at selecting out a transition population where they're kind of in between the star forming cloud and the quiescent cloud. Oh, too far. So then we're trying to look at comparing the cluster population of these transition galaxies with the field population in order to figure out what's going on in clusters. So here you can see that I've plotted in this top panel the distance from the cluster center for the 3 different populations, Green Valley, blue quiescent galaxies, and post-starburst, and then plotted their ratios at each of those distances. So the gray band here is the field galaxies. So the idea is to look at the fraction of the galaxies that you're seeing versus the total in the cluster compared to that in the field. And so you can see here that the population of post-starburst and Green Valley galaxies doesn't change a whole lot between the cluster and the field, which is somewhat surprising if you think that something about the cluster environment is what's pushing these galaxies into the transition into the quiescent sequence. And with the blue quiescent galaxies, you see more of a trend with radius. If you compare this to the fraction of the quiescent galaxies, it's more similar to the quiescent fractions, which makes sense when you consider that this box was drawn around the blue part of that quiescent sequence. So they should be similar to it if we're selecting a subset of them. So yeah, I've summarized this in a table down here if it's a little bit easier to understand with the specific numbers themselves. So you can see that we're not detecting much of a change in the Green Valley or the post-starburst. We see more of a trend in the blue quiescent galaxies. And so the idea now is that what we want to do is model these galaxies in order to find out how long they're spending in this transition period in order to get a better idea of what processes could be going on in order to push them into this quiescent cloud. So yeah, that's mostly what I wanted to cover here. I wanted to make it short and sweet so that we could have a little bit of time for discussion. So yeah, thank you.
Great, thank you, Karen. Interesting stuff. Again, we can take a quick question or two if there's one right now. And if not, we can come back to this in the discussion. I think there's lots of interesting things to talk about how this relates to stuff we heard yesterday. Yes, hi, Howard.
Looking at the table, I would say those 3 sets have similar trend. In the sense, if you plot this, the fraction in log scale, I don't think that difference. You really need to plot them in log scale to tell whether they have a similar trend or not.
So you mean a log scale
on the y-axis?
On the
so you can see that you look at the number, fraction. Right? They are sort of down by about a third, going from inner to mid cluster, and so I think in log scale it would have sort of be consistent with probably consistent with the air bar having a similar slope.
Yeah, I understand what you're saying. Yeah. I think one of the interesting questions with regards to these transition galaxies is what is the right thing to put on the denominator? It depends a lot on what your hypothesis is for what's happening. And so, for example, if you think that these really are transition galaxies going from the blue to the red population, then what might be interesting is how many of them there are relative to the blue population. And that, of course, decreases as you go towards the center. And that means that the fraction of all these things relative to that parent population increases more strongly towards the center. And that's
So these are fractional relative to the whole sample.
that's right. Joel, I saw your square light up. Did you want to say something? Or?
Yeah, thanks, Michael. Yeah, so this is Joel Roediger from NRC. Very nice work, Karen. I'm curious about the your definition of the blue quiescent population, and whether, I mean, would it imply any kind, because this is supposed to capture a fast quenching population. So, and I apologize if you said this, covered this in your talk, but do you see overlap in the blue quiescent population and the post-starburst population?
Yeah, so if you look at this diagram here, forgive me, this plot is a little hard to read. I'm still working on the best way to depict this information. So the circles that have yellow outlines are the blue quiescent galaxies defined in UVJ space. And these purple squares overlaid over top are the spectroscopic post-starburst. So you can see that we get a few post-starburst galaxies in all of the different populations that we've defined here, where the blue quiescent galaxies has an overlap with everything.
Okay, and second question is, have you cross-matched your results with Christy Webb's results on the ages of these galaxies? And are there any kind of distinctions between the different populations in terms of their stellar population ages?
So I was looking at, when I was first focusing on the blue quiescent galaxies in order to figure out where best to draw those lines, I was looking at Christie's ages in order to get an idea of where that boundary should be. I haven't looked at the ages, I don't believe, for the other populations, but for the blue quiescent galaxies, her age gradient along the quiescent sequence seemed similar to that in Belly, which is how we defined those original boundaries for the blue quiescent galaxies.
And,
At this point, oh, sorry.
Just one of the challenges is, so far I've only fit the quiescent galaxies for their star formation histories, so that would only select a very small fraction of the galaxies that Karen's looking at. But it's definitely the plan.
Yeah, oh, thank you for reminding me, Christy.
Yeah, Christy's currently looking into sort of the next step is doing that same modeling for looking for things that have truncated star formation histories by fitting all the galaxies. There's of course a whole other host of challenges in trying to fit the histories of things that have recent star formation. Great. Well, sorry.
Can I ask one? Is that cool?
Sure, that's cool.
Can you show the stacked spectrum of the Green Valley? What do you think of this thing?
Beautiful.
I think Michael's the best one to touch on this.
Okay, well, here's what I think. I think if you search the Sloan Digital Sky Survey, finding spectra like this in the local universe will be almost impossible. I bet $5 on that. This is really weird.
No, these are just the E bracket A things that Bianca found back in the day, and we found in CNOC as well, right? I mean, they look like E+A galaxies with emission lines, and there's a number of different.
Yeah, but the strength of the emission line is the weird thing. Yeah, I mean, I agree. You can find things with H delta and a little bit of O2, but that's a fair bit of O2. I would be willing to bet that it would be hard to find spectra like this in Sloan. I could be wrong.
Interesting.
But I don't know. I guess, I was waiting for Sean McGee to pipe up, but he's the strong silent type. But to me, this is like overconsumption.
These are spectra that are very common in distant clusters. They're also quite common, but not that common in the distant field. So if you compare, is this a stacked or is it an individual spectrum?
Stacked.
This is stacked, okay. So from the stacked, you cannot really judge. But I mean, if individual spectra would have these signatures, we did a lot of study back in the days. This is a result of dust, actually, because the dust obscures the emission lines more than the older populations. And what you get is something like this. That was the interpretation we had. But these are typical of distant clusters. There are many of them, what we call the EA.
But how could this be dust, Bianca? Because if you tell me the real O2 underlying this is much higher, then I've got a star-forming galaxy with an old stellar population and a huge amount of H delta. Like that's probably H delta of definitely greater than 5. How can I have lots of star formation and yet strong H delta?
The dust is obscuring the O and B stars.
The dust is obscuring the youngest generations. There is a whole picture of which I can send you now. Probably we don't have time to go into details about this.
Well, I read all your papers when I was young.
we see this in other.
I read them all.
We see this in other galaxies where you've got lots of dust obscuration. These are not cluster galaxies; these are kind of much more pathological. But they've got lots of dust obscuration because we see lots of dust emission.
You know, locally,
but they also have a little bit of O2.
Locally, these spectra are only found in luminous infrared galaxies and ultraluminous infrared galaxies. If you take local ultraluminous galaxies, they look like this.
That's my point, not Green Valley galaxies. So why are you finding, yes, these are Eulergs. I agree. This is what a Eulerg looks like, which is a starburst that's obscured on top of a whole bunch of post-starburst. Finding a whole chunk of these in the Green Valley in a cluster is weird. I mean, this is what our money looks like, right?
Well, there are lots of guys with this spectra, I mean, galaxies with this spectra in distant classes, and by distant I mean 0.5, 0.8, which is what we did with the Morse and with e-disks later. These have a wide range of colors anyway. I mean, you also have blue ones that are like this. Only if she takes the Green Valley and looks at the majority, again, we should see the individual spectra because the stacked one can be a bit misleading.
I completely agree with that statement. Well, you know, it'd be fun to settle this little debate. I was only going to propose that this is what overconsumption looks like. This is exactly what an overconsumption galaxy should look like in my mind, where the O2 is an AGN, right? AGN simultaneously quenching with ram pressure stripping gives you massive H delta. And lo and behold, it's also in the Green Valley. So I thought Sean would be jumping up and down. I could be wrong. You're right. Maybe this is common. This is just dust, but I don't know.
And is that neon 5 popping up at the blue end? I forget where neon 5 is. Renee? I see a little, which is what you would get for an AGN. I'd like to, yeah.
Sorry, we don't have time.
So I think it's neon 5 is 3, 4 to 6. So I think it's outside of this range.
Right. I think this is good discussion to have both later and also in the closed Go Green session later. There were a couple of questions, a couple of raised hands that I'd like to take if just delay things a little bit longer. Kate Rollins, you had your hand up.
Actually, Joel asked my question. I was gonna ask about the overlap between the samples, but just like to say, this is very nice work, and yeah, I agree. The O2 is pretty strong in that stack, but it's not untypical of quenching and quiescent galaxies at those kinds of redshifts. If you look in like Legacy or Vipers, for example, it's pretty common to have O2 emission in these quenching things, but yeah, it does seem to become weaker at lower redshifts in Sloan.
Can I just give a suggestion, then I shut up? Why don't you stack the Green Valley galaxies, you divide those with O2 and those without O2, and you stack them separately?
Yeah, could do that. Okay, I'd like to take one more question before we move on. Rowan Hagar had your hand up.
Yeah, hi, thanks. Thanks very much for the talk, Karen. It's interesting. Yeah, sorry, I'm Rowan from Nottingham, by the way. I wanted to ask a little bit about on your final slide. It looked to me like you were defining your field galaxies as things outside of 1.5 megaparsecs. Is that right? Is that how you're or is that just the way that you're plotting this?
No, that is how I'm selecting them. We worked with a couple different ways on how to best select out the field galaxies, and this is what we had landed on for the moment.
Okay, because I would have thought that 1.5 megaparsecs, you'd be getting a lot of contamination from things like maybe backsplash galaxies at that kind of radius. I was wondering if that's something you'd thought about, or if you tried working out these fractions for, air quotes, a true field sample, rather than what I think is relatively close to a cluster.
Yeah, we had talked about using a separate sample for the field galaxies. I believe we had talked about using UltraVista. Michael, can you confirm?
Yeah.
Yeah, so we were working on trying to get that to pull our field sample from instead of selecting it at a harsh radial boundary.
Right. Yeah, I'd just be interested to see that, because I'm looking particularly at your post-starburst, for example, where you've got a comparable fraction in your field to what you've got in your kind of mid-cluster. I'd be interested to know how much of that is contamination, like I say, from things like backsplash galaxies, and how much of it is actually sort of intrinsic.
Yeah, that's a good point. I agree.
Okay, thanks.
Okay, thanks. It's good discussion, and it'd be good to come back to this. I think it's there's lots of things to talk about here. But the last science